So we're going to have some quantum gates that are universal, though, right? We love universal gates. We can do anything with them, and that's why we love them. So what we're going to show is in chapter 4.5.1, the first thing is that so-called two-level unitaries are universal. So 4.5.1, two-level unitaries are universal. Before we get into the weeds, and I'll explain to you what I mean by a two-level unitary, just a sort of roadmap overview. This is the first thing that we're going to show. So we're going to have these things which we call two-level unitaries are going to be universal. And then we're going to show that we're going to be able to implement these two-level unitaries with things that we know and love on quantum computers, single qubit operations, and two-qubit gates, C-NOT gates. So again, we're sort of iteratively building up what we can do in a quantum circuit based on what we already know how to do. In this case, we're going to start from a sort of top-down approach. We're first going to do two-level unitaries, show that they're universal. And then we are going to show how we can construct those out of single qubit gates and C-NOT gates. So here's the example that's going to guide us through this. We're going to have a 3x3 matrix, A, B, C, D, E, F, G, H, and we'll skip to J because we have I reserved for the imaginary unit. And it's going to be a 3x3, just for sake of having less writing. Usually, we're powers of 2, at least in this course. So in this example, we'll have a 3x3 matrix. So what we're going to try to do is we're going to try to compile this unitary. That means we're going to try to find a sequence. So we want to find a sequence of unitaries, U1, U2, and so on, some number, let's call it little m for now, such that this product is equal to the unitary that we want. A nice way to rephrase this, which is very simple, but helps you get some traction into how to actually do this, is to rewrite this as U, and then I'm going to multiply it by this inverse. So it'll be U, M, dagger, so on, U2 dagger, U1 dagger, is equal to what? The identity. Okay? So this is nice because it gives me a strategy. I want to find some unitary matrices such that we're making this unitary that we want look more like the identity matrix via matrix multiplication. Okay? Once we do that, then these are equivalent. Then I just multiply by the inverses, and I have the sequence of unitaries that I want. That's we'll come to call it the compilation of the unitary, the sequence of unitary that, upon multiplication, constructs what we want. Okay? So have you seen how to do this with matrix multiplication before? You've probably seen it with Gaussian elimination. If I want to zero out some matrix elements, you can add a multiple of one row to another, for example, and do this. So hopefully that's familiar. But there's also a way to do it via matrix multiplication. And I want to motivate that by having you actually work it out. So what I'm going to do is I'm going to set U1 to be the following matrix. Let's set U1 to be, in terms of the matrix elements U that I have, 1 over mod A squared plus mod B squared. These can be complex numbers. And then we'll have A star, B star, B, and minus A in the upper left block, zeros elsewhere, and a 1 in the lower right. Okay? So why are we normalizing by this? It's to make it so that this is a unitary matrix, okay, for whatever A and B are. And so you could check that every column has unit norm and every row has unit norm. And then the third column is there's a 1 in the lower right. And so the third row and the third column also have unit norm. So this is indeed a valid unitary matrix. And now what we're going to do as an exercise is I would like you to try to work out what happens when we left multiply U by U1. So let's evaluate U1 times U. Now, you might be thinking, after spring break, 3x3 matrix multiplication, kind of mean. So focus on this second element, the down to over 1 element in the matrix. That's the one that you should see go to 0. So I want you to work that out. And then you can work out the others, if you want to or if you have time. But that's the one that's going to be important to us. So take a minute to try to work out this matrix multiplication. When you do this, you should see that one of the matrix elements is 0. Let's see why that is. So I'll write it out explicitly just so that we can see it. So u1 on the left, 1 over this normalization, mod a squared plus mod b squared. And then we have this unitary a star, b star, 0, b minus a, 0, 0, 0, 1. And then the unitary u itself is a, b, c, d, e, f, g, h, j. Okay? So the one that's of most interest to us is we're going to do the second row. Do I have another color? I do. Second row by the first column. Second row, first column. That's the 2, 1 matrix element of the result. And hopefully now you can see that I'm going to get a times b plus minus a times b. And so that's going to be 0, right? The other ones I don't necessarily care about. So what we're going to do is we're just going to note that this matrix element is 0. That's what I care about. And then let's call the other ones some new matrix elements. A prime, b prime went to 0, so we'll have a c prime, d prime, e prime, f prime, g prime, h prime, and j prime. Okay? Does everyone see this? This is nice. Now we have a result that's starting to look more like the identity matrix. We've zeroed out one of the matrix elements in the first row. Now I would like to zero out the second one. Before that, just a note. Why are we calling this a 2-level matrix? Well, note that U1, I'll sort of use the linear algebra notation here. So let's have E1, E2, and E3 be the standard basis vectors. Look what happens when I apply U1 to the first basis vector, E1, just for concreteness, I mean 1, 0, 0. So that's going to be written as a combination of E1 and E2, right? So that's equal to A star E1 plus B star E2. Similarly, U1, E2 will be equal to B E1 plus minus A E2. And then finally, U1 on E3 is just E3. Okay? So what does it mean to be a 2-level unitary? Notice that the action on the first and second basis vectors only involve the first and second basis vectors. Okay? So there's 2 of them. So that's what we mean by 2-level. And then every other basis vector, in this case there's only 1, is not going to be involved. It's not going to be changed. So it's 2-level in the sense that we could think of this, once we normalize it, I omitted the normalization, as a 2-by-2 unitary. It's just acting on a certain column and row in the matrix. Okay? So that's what we mean by 2-level. And we're going to be able to do this again. Now what's going to be our strategy? I want to zero out the C prime in the lower left. Then I'll have only an A prime in the top right, and then the rest will be 0. So that's looking a lot more like identity. In order to do that, we can choose U2 to be equal to something that looks similar. 1 over the square root of A prime mod squared plus now C prime mod squared. And then the 2-level unitary in this case will look like the following. A prime star, 0, C prime star, 0, 1, 0. And then I'll have C prime, 0, minus A prime. Okay? So a similar strategy you see. Take the complex conjugate, normalize to make it unitary, and then 1 comes with a minus sign, so that when you do the matrix multiplication, you'll get, well, in this case, A prime times C prime plus minus A prime times C prime. So that's the one that's going to go to 0 again. So this, I'll just leave it to you to check. So check that. If I introduce this on the left now, I'll get U2, U1 times U. And this will be, we will have some new number, let's call it A double prime for the moment, and then zeros everywhere else in the first column. And that's what we wanted. Then we'll have D double prime and G double prime. And in the lower right block, E double prime, F double prime, H double prime, J double prime. Okay? Now, this U1 and the U2 are unitary matrices by construction. They're two-level unitary matrices. And so U being a unitary matrix itself, that's what we want to compile. The product of unitary matrices will also be unitary. Okay? So the thing that we have on the right is also going to be a unitary matrix. Unitary matrices have column norm equal to 1 and row norm equal to 1 for every row and every column. What does that tell me about some matrix elements in this new product on the right that we got? Exactly right. A double prime is going to have to be 1. Why? Because this first column has to have norm 1. So we can say right away that this A double prime has to be 1. Very good observation. And now there's something else that we could say. Exactly right. This row also has to have unit norm now. Okay? We have a 1 here. So what does that say about D double prime and G double prime? They have to be 0. So we have zeros in the first row. Okay? That's looking a lot more like the identity matrix. Okay? So two matrix multiplications. In general, this is going to be the strategy. For however many matrix elements you need to zero out in the first column, which will be like the dimension of the unitary minus 1, you'll be able to construct the sequence of two-level unitary matrices that you can zero all of them out. When you do that, you'll also zero out the first row as well by the constraint that it has to be unitary. So the last one, in order to actually get it to be the unitary, to be the identity, will be the following matrix. Just to write it out, we'll have U3 as another two-level matrix. So this will be 1, 0, 0, 0, 0. E double prime star. Let me make sure I have this right. I think I have this right, but I might be missing a minus sign. So E double prime star, F double prime star. I think it should be minus H double prime star, and J double prime star. Leave it as an exercise, I guess, for you to verify this. You might have to modify this a little bit. But point being, it'll again be a two-level unitary. When we multiply by this, we'll get the identity matrix. And you might have to normalize this as well. So finally, what we have is that U3 times U2 times U1 is times U is equal to the identity, meaning that U is equal to U1 inverse, U2 inverse, U3 inverse.